Supervised machine learning. In supervised machine learning, you're given a dataset with its annotations, and you want to, from these annotations, learn how to make annotation for future examples. Here's an example. You have a couple of patients that some are suffering from a disease and some are not. And you have measured two different variables for them. In this case, the variables are called HDL and LDL. Now you want to make a decision line, that is a way to tell healthy from disease patients. So you would draw this as a sort of a separating plane between the two patient categories. I represented it here by a dotted line. The purpose of this is when you receive a new patient, you want to determine if this is a healthy or a disease patient. The goal here is to make a classifier that can tell, given a new patient and its HDL and LDL, would this be a healthy or a disease patient? What would be the best estimate? And of course, this could be, you could think about this in other settings than HDL or LDL. You could look for different mRNA scores, like what's the expression value of different mRNAs. And normally as well, we look on more high-dimensional spaces than 2 dimensions. But for the simplicity here, I just selected 2 dimensions. So the problem when making this decision boundary is we have to make an optimal choice here. We need to make a decision boundary that either becomes very complicated and really try to cover as many patients in the right category as possible, or we would sort of rather select something that's a less complicated decision boundary that will now as well have a couple of caveats. In this particular example here that I demonstrate, it's we have a couple of patients here that are wrongly classified by this green line, but the real test of this is how well this generalizes. So actually, again, given a new patient that we receive, would it classify it correctly or incorrectly? One way to do this with linear functions, or in multiple dimensional, a linear separator would be a hyperplane actually. So we could design classifiers based on hyperplanes. So we would like to select a hyperplane that gives the maximal separation between our two classes of patients. And I've taken this example from Wikipedia where we have 3 different separating hyperplanes, and both H1 and H2 gives you separation between the 2 different patient categories. However, hyperplane 3 does not give such a separation between them. But one could still argue that H2 seems to have a better property because it gives you the largest margin between the 2 different classes. If you add the distances between the nearest examples to the hyperplane, you will see that H2 here gives a better separation. So this is the idea behind a support vector machine. A support vector machine can be designed to select the maximum separating hyperplane, but as well does so by allowing some examples to push the way through the decision boundary and sort of allow us to do so in a way that we can penalize those examples rather than sort of designing the whole hyperplane based on this. And yet another thing with support vector machines is that we can use so-called kernels as well in this. This is a way to warp the space if we want to make non-linear decision boundaries. And I will come into all these concepts in the following slides. First out, a maximum margin hyperplane. So this is a way to select a hyperplane that will give you the maximal separation between are two classes of observations. So you would sort of select the hyperplane in a way that it's giving you the maximal separation. And that turns out to be the separation turns out to be the same thing as 2 divided by the coefficients of the hyperplane W, and this actually means that optimizing or to maximize that hyperplane, it means actually minimizing the norm of W. It turns out that this maximum margin hyperplane will it will always fall on this selection of 3 different data points. Hence, and these are known as the support vectors of hence the term support vector machine. Yet another part of the support vector machine is the so-called hinge loss function. This is not a necessarily part of there are hard margins support vector machines as well, but often you use this hinge loss function where you can use where you penalize only up to a point. So you penalize examples that are misclassified, but not the ones that are correctly classified in the training function. So you're not trying to sort of give extra credit for examples that are more than well separated. So, for instance, in the bottom right corner, you might expect that you will get an extra plus, but you don't get an extra plus to the minimizing function from this. In total, optimizing a support vector machine is surprisingly simple in its mathematical formulation. It's just to minimize the function here to the right. That is the sum of the hinge losses of your examples. In this notation here, we assume that the examples or the input vectors of the examples are given as x vectors, and we are trying to and the desired outcome of them, or for instance healthy or unhealthy, are given as yi variables here, and where yi is either +1 or -1 depending on the class. And we now try to optimize this function based on different values of W that will give you the best value. This observe here that this contains a hyperparameter lambda as well, and the function of the lambda is now to sort of put a weight between how much you penalize the incorrectly classified parts, the hinge losses, versus the maximum margin. How much weight do you put on those two different things? A support vector machine can be combined with the kernel as well. So rather than taking direct input from the weights, we can as well convert our features into a space where they are better separatable. Here I demonstrate this from an example from Nobel 2006 Nature Biotech. Here we want to separate red and green dots, where the red dots are centered around 0, and it's impossible to select a separating hyperplane that would separate this based on just expression value alone. However, if we would introduce a kernel here, that gives you yet another dimension in our classification space, we would now get not just expression, but expression times expression. In this new space, it's super easy to make a decision boundary, because we can now make a boundary based on the quadratic expression. This would allow us to, with one single separating hyperplane, make a distinction between the red and green dots. Once we trained a support vector machine or any other supervised machine learning method, we want to be able to assess how well they perform. As we want to be able to detect symptoms of overfitting, we need to train our methods based on examples that are not sitting in the same data set as we were training our machine learning algorithm on. So we wanted a separate test set. And often, in many situations, we end up wanting to optimize hyperparameters of our method. For instance, the lambda function here, or the slack penalty, and the prior examples of support vector machines. We want to optimize that, and that's often something we want to do on a separate, yet another separate test data set. So this means that we need large data sets that are completely separate from the ones we use for training. And a common trick is to economize this, because often supervised examples are expensive. It's often hard to produce supervised methods because we supervised data as this often involves manual annotation. So often you want to economize on the training data, and one way to do so is to do so-called cross-validation. This is sort of a way to eat the cookie and have it left for the day after as well. So here's an example of threefold cross-validation. Training the cross-validator will involve firstly separating the training set into 3 different bins. So these different bins will, or so-called cross-validation bins, will fill different function for the different learners. So first you will train your first learner based on the 2 first bins and test it on the 3rd bin. You would then train a second learner based on the 1st and 3rd bin and test it on the 2nd bin. And finally, you would train learner number 3 based on the 2 last bins and test it on the 1st bin. So based on this example, we can now give an accuracy estimate based on all 3 our training and test data, without actually having trained on the same examples that we tested. Sometimes you even combine this with what's so-called nested cross-validation, and this is often used for instance, for if you want to assess or if you want to select hyperparameters. In such case, you will further divide your training examples into yet 3 different cross-validation bins. So you take your first 2 trainers here for learner number 1, and you would divide that into 3 different bins, whereof the 2 first ones are trained are used first for the first learner inside an internal cross-validation. Then you would sort of do the same for a second internal cross-validator and a 3rd cross-validator, and actually allowing you to assess hyperparameters based on the full 2/3 of the original data. Of course, you repeat this for learner number 2 and learner number 3 as well. So how do we measure performance for classifiers? Say that we have trained a classifier and the output of the classifier is a score. We also have our different data points that we have want to test on. So these are either positively or negatively labeled. Our classifier score can be thresholded in such a way that we say that everything above this threshold is something that we predict as positive outcomes, and everything below the threshold is predicted as negative outcomes. So now we want to measure how well this threshold and this classifier works. The way we represent this is in a function that we call a confusion matrix. So we just align, we make a matrix out of all the examples that we have predicted as positive and negative versus the ones that truly being positive and negative examples. Examples that are correctly predicted as positive examples, they are called true positives, and false positives are incorrectly predicted as positive examples. Similarly, we can say that incorrectly predicted as negative examples, we call them false negatives, and the ones that are correctly predicted as negative examples, they are true negatives. These are often compressed into different measures like precision and recall and specificity. You also frequently see false positive rates, FPRs. This has the same shape as and form as a p-value. You as well can look at true positive rates, TPR, and false discovery rates, FDRs. Sometimes you see something known as receiver operating characteristics, and this comes from a setting where we allow our threshold in a classifier to vary. So depending on how we set the threshold in a classifier, we get different false positive versus true positive rates. So these are often reported as these rock plots now, the true positive rate versus a false positive rate of a method. And since a random observation here of this would be going according to a dotted line, the dotted line here in this example, that is as an area under the curve of 0.5. So if you integrate the triangle, you would get an area of 0.5. We often see something known as the ROC score of a method. That is the integration now of the true positive rate versus false positive rate. And any value above 0.5 would be seen as a good predictor.